This is a problem from our lab assignment section 4.3. Here we are given the following function. It's 200 plus 8x to the third plus x to the fourth. And this is going to be a long list of things to look for so that we can get an idea of how the graph might look like. Step number one is asking us to take the derivative. And so the derivative of a constant is 0. And now we have 8 times x to the third power. So bring the 3 down. 8 times 3 is 24. And then subtract 1 from the power. That would be 24x squared. And then we have a plus and 4x to the third power. That's our derivative. And then it's asking us to factor the derivative. So if we factor this, we get a constant that we can factor. I think the whole number constant that we can factor is 4. We factor out an x squared, as they have over here. And then if they factor out an x squared and a 4, 4 out of 24 is going to be 6. And then x squared out of x squared is just 1, so it's just 6 times 1. And so g prime is equal to 0. It looks like we're going to have a couple of solutions. When x squared is equal to 0, that means x is equal to 0. And when x plus 6 equals 0, then x is going to equal to negative 6. So we have a couple of solutions. These are your critical points. That's when the first derivative is equal to 0. Alright, in our step 3, they're asking us if g prime of x is equal to this factored form of the derivative. That's 4x squared times 6 plus x. We know that we know that 4 times x squared is always positive. So the only thing we want to look at to see if g of prime of x is positive is x plus 6. So it's positive, and then the original function is increasing. If so remember, at 0 there's nothing happening, and so we just care about when this thing is positive. So if we set this thing greater than 0, we can solve for that by bringing the 6 over to the other side, so it'll be x is going to be greater than 6. However, g prime of x is negative and g of x is decreasing if, again, x is not equal to 0, and this time we have the opposite relation for negative 6. Therefore, we can determine the interval of increase. So the interval of increase is happening here when g prime of x is bigger than 0, and that happens when x is bigger than negative 6. So we want to be bigger than negative 6. In interval notation, it'll be minus 6. Now, we would normally like to go to infinity here. However, there's an issue because we're not including 0. So we're going to stop off at 0 first, and then we're going to take the union, and then we're going to go from from 0 to infinity. And that would give us the places where it's increasing. Which means that at 0 it's probably not going to be a maximum or a minimum. In fact, it might be an inflection point. We'll see that a little bit later. Determine the decrease. Decrease is when x is less than negative 6, so that's going to go from minus infinity to negative 6. So now that we have the intervals of increasing and decreasing figured out, we can identify the local max and min. It looks like it decreases on the left side of negative 6 and increases to the right side of negative 6. And so this, when it goes and decreases and it increases again, it looks like it's going to be a minimum. And they give us, so it was nice enough to give us the value of negative 232, where we have a minimum. So there's no local maximum here. At 0, there's a 0 slope, but it's not max or min. Alright, step 2. It's increasing on both sides of 0, then so it goes up, it increases and keeps increasing, and g of 0 is equal to 200 is a not it's neither a maximum nor a minimum because it's not changing directions. So determine the local minimum values. So the minimum values they gave us here is negative 232. So that's our local minimum value. And determine the local maximum value. I think we've already said that this is not a maximum value, so we can go ahead and call it DNE. And then that takes care of max mins. Now let's take a look at concave up and concave down. We have the unfactored form of the derivative will help us find the second derivative a little bit quicker. We take the derivative of this thing, 24 times 2 is 48, and then we subtract 1 from the power, that's just going to be x. And then we have plus 4 times 3 is 12, x to the second power. So that's our second derivative. We're going to figure out when our second derivative is equal to 0 by factoring like we did before. And so we take a 48 out. Well, I don't think we can take a 48 out, but we'll take a 12 out and an x out. So the first term, we got 12 out of this, we're going to have 4 left, and we took the x out, so that's gone, so we just have 4. And 12x, we took the 12 out and one of the x's, so it's just an x. So g double prime of x is equal to 0 when either x is equal to 0 from here, or when x is equal to 0 from this expression 4 plus x. And if you set that equal to 0, you're going to get a negative 4. So those are, well, they're possible inflection points, but we're not sure. So we'll check it here now. When x is less than negative 4, so let's take a look at the factored form here. That's 12x and then 4 plus x. When x is less than that, this first part would be negative, and then if we put a number that in for x that's less than negative 4, it'll be 4 minus, or 4 plus a number less than negative 4. That would make that negative also. So negative and negative would be a positive. And so g prime would be concave. Positive is concave up. Between negative 4 and 0, it's still going to be negative for the first factor. And then if we put a negative number here that's between 0 and negative 4, like a negative 2 or something like that, this would be positive. So a negative times a positive is a negative, which means it's concave down. And then this is also going to change concavity. When we put a positive number, we get a positive and a positive, and that would be concave up. And so now we can figure out our changes in concavity. 0 is an inflection point because it goes from positive, well, the 0 is right here, it goes from negative to a positive, and so negative to a positive will be an inflection point. And negative 4 goes from a positive to a negative, so that is also an inflection point. So the inflection points are as follows. The smaller inflection point here is negative 4, comma, and then 0, comma. 0 is just going to be 200. So the other one, we need to put negative 4 into this equation. So let's see, I'm going to take my Excel sheet out and I'm going to put in the value. This is 200 plus 8 x to the third power plus x to the fourth power. So that's my function, and I just wanted to write my function out here. So my function, I'm going to put an equal to, it's 200 is a constant, plus 8 times x, so this is my x raised to the third power, and then I have a plus, and then my x again raised to the fourth power. So that's 200, but if I put in a -4 here, my output value is going to be -56. By the way, the other value that we had before was -6. So if we put a -6 in there, we're going to get a -232, which we already got earlier. So our y value here is -56. And now we want to determine where the intervals where it's concave up and concave down. So let's do concave upward first. And we want this concave up. So it's positive when it's less than 4, so that would go from -infinity to -4. And then we're going to union it. And then the other positive part happens when x is bigger than 0, so it's 0 to infinity. And then it's going to be concave down between -4 to 0. Okay, so we have the inflection points at -4 and 0. We have the places where it's concave up and concave down. We even have the values, the y values. And so they want us to sketch the graph. So check your work with a graphing device if you have one. Let's actually plug it in. Here's our graph. We got y is equal to, we have a 200 plus, let's take a look again, 200 plus 8 x to the third power plus x to the fourth power. So I think that's it. 8x to the third power plus x to the fourth power. Now clearly this is not getting us anywhere. We do have some information about the max and mins. This can go as low as -232 and 200. So maybe we'll go with that. Let's set up our axis. Maybe this went all the way, the important points went up to -6 and 0, so let's go 5 here. Then we don't need that much. -232, so let's go -300 here. Let's try that again. That's -300, and let's go all the way up to 500. And we know 200 should be at the intercept, but let's go all the way up to 500 so we can see the bigger picture. Okay, we seem to have lost our function here. So that's again 200 plus 8 x to the third power plus x to the fourth, and here we go. So our graph here, we didn't show this, but if we solve for this thing when this thing's equal to 0, we would have gotten our two points of intersection, the x-intercepts, and we have our minimum value -6, 232. We have our other critical point, which was not a max or a min, but it turned out to be an inflection point. We do have another inflection point at -4, so let's see if we can trace that out. So somewhere over here, -4, -56 is another important point. That is another inflection point that we have. This is how our graph would look like if we go back and select the correct graph. Hopefully we can pick a graph that looks like that. So it goes down, it crosses a 200, we have an inflection point at -4. This looks awfully close. Let's go check the others. Nope, I think this is it. So this thing drops down to -200, and so when x is equal to -6, we have the local minimum. We have that flat point over here. We have an inflection point at 0 and an inflection point at -4. Okay, so I think this is it. And there we go. We got it correct, and that's this problem.